Welcome. In today's video we're going to discuss finding the equation that will give us the area of the portion of the circle above a chord. So in a formal statement we might say that given a circle of radius r, find the area above the chord, and I'll just denote that area above the chord, this blue shaded portion in the figure here, as A, capital A sub c, where the chord is at a height of y equals h, and h of course is bounded between the origin and the radial dimension. Okay, so let's just go ahead and label the figure that we have a little with some of the symbols here a little bit. So we have the x-axis, the y-axis. We are told that the circle has a radius of r, so I'll put that down. And we also know that the chord is at a height y equals to h. And another thing that we know, and we've seen this a few times already in our past videos, is that the equation of a circle of radius r is given as x squared plus y squared is equal to the radial dimension r squared. Okay, so if I were to solve for x, I could say that x is equal to the plus or minus the square root of r squared minus y squared. Okay, where the plus root is obviously for those x values in quadrant 1, which are positive, and then the minus root are for those values of x in quadrant 2 as pictured here, where x is negative. The way I'm going to solve this problem, though you could do the entire blue portion, I'm going to find the area of a differential strip in quadrant 1, and then I'm going to double that result. So I'm going to confine my analysis to just quadrant 1, and I'm going to take a differential strip here, namely this one, and the differential strip is going to have a differential height of dy. And so to find the area of this differential rectangle, let me put that out here, I'm going to just call this differential rectangle dA sub c for the differential area of the chord that we're interested in. It's going to be the length of that rectangle times the height of that rectangle. And so I need to know what this dimension is, and I also need to know what this dimension is. Well, this dimension I know is just where x is 0, so there's no problem there. And this dimension here is what we just found when I solve for x over here for the equation of the circle. It's just the positive root r squared minus y squared. Okay, so in fact the differential area of that rectangle is nothing other than this dimension minus this dimension. That gives me the length of that, so that's going to be root r squared minus y squared minus the 0 times the height of that, which is dy. And since I'm confining my analysis to quadrant 1, but in fact I want the blue shaded portion of this entire region, which encompasses quadrants 1 and 2, I'm going to double that result. So that way, like I said at the beginning of the video, I just want to focus on quadrant 1 and take advantage of the symmetry of this problem by just doubling the result. So dA sub c is 2 times radical r squared minus y squared dy, where our y is going to range between the value of h at the bottom here all the way to the top where y is all of the radial dimension r. Okay, so to solve this then I need to integrate both sides, so my abbreviation for integrate both sides is IBS, and the integral on the left of d of anything is that anything portion, so it's going to be a sub c, which is what we're after, is equal to, I'll take the 2, which is a constant outside of the integral, of root r squared minus y squared dy. And now I'll put in the limits of the integration. Y ranges between the height of the chord to the full radial dimension at the top. Okay? And now the question then becomes, how do you evaluate this integral? Because it looks pretty complicated. And of course, a way to go about analyzing this integral is to do a trig substitution. Right? So we will evaluate integral using a trig substitution. And before I do that, let's just remember a trig identity. Okay, so we've also talked about this trig identity many times, and this is one that I think all of us know. The trig identity I'm referring to, of course, is the sine squared of theta plus cos squared of theta is equal to 1. That means that cos squared of theta is 1 minus sine squared of theta. Okay, and when now coming back to this idea of the trig substitution, you've probably learned this in your calculus class. What you want to do is you want to find a couple of things for which you're going to let y be. So in particular, when I say let y be, let y, I'll get it right here in a second. Okay, let y be equal to, the first thing you want to look at is, well, we have here, let me do this in blue, you have here a constant value of the radial dimension, and so I would like my y to have that radial dimension r, so that when I square it, I'm going to have a common factor of r squared. So that's one thing you want to look for when you're doing the trig substitution in these sorts of problems. The second thing is what we did up above, where we noted that that 1 minus sine squared can be written as cos squared, and in fact when we do the squaring and then taking out the common factor of the r squared, you will get a 1 minus r 1 minus sine squared type of a deal if you let y be r times sine of theta. So that means that when I square both sides of this, y squared is going to be r squared times sine squared theta, and when I differentiate this, I'm going to get dy is equal to r cos of theta d theta. And now let's go ahead and plug these values back in. Okay, so let's do that here. I'm saying that a sub c, which is what we're after, is equal to 2 times the integral of, and we're going to integrate now not with respect to limits on y, but limits on theta. So I'll just put a theta here as a placeholder. That reminds me that we're changing our variable here. It's going to be radical r squared minus y squared, we said, is equal to r squared times sine squared. And then we said that the dy is this right here, so that's times r cos of theta d theta. Okay, now let's go ahead and factor out the common r squared there. That becomes 2 integral with respect to this variable theta of radical r squared is the common factor there, 1 minus sine squared theta times r cos of theta d theta. And let's go another step. So this is going to be 2 integral with respect to theta Radical r squared is just r. Radical of 1 minus sine squared theta, we said up above that 1 minus sine squared theta is in fact the cos squared theta, so let's use that result. So we get radical of cos squared is just cos theta, so all of this reduces to that, and then times, of course, we get all of this r cos theta d theta, and so this then is 2 times the integral with respect to theta of, we get an r times an r, that's a r squared, and it's a constant because the radius is constant, cos times a cos is a cos squared theta d theta. Alright, so now we ask ourselves, well, how do you integrate cos squared theta d theta? And here we then have to do a little bit of an aside, and I'm going to, I've actually shown how to do this in a previous video where we were looking at the area of a circle, and in that video I used integration by parts, so that was a technique to solve something like of this form, integral of cos squared. I'm going to illustrate a different technique using the double angle formula here. So let me make a small aside here. Alright, so aside, double angle formulas. So these say that, and these are things that you really would do well to just memorize. Cos of a plus or minus b is equal to cos of a times the cos of b, and then the signs flip, it becomes minus plus sine of a sine of b, and sine of a plus or minus b is equal to sine a cos b plus or minus, the signs are preserved, sine of b cos of a. So therefore cos of theta plus theta, which you will recognize is of course cos of double angle 2 theta, is equal to, as per the formula up above, it's going to be cos of theta times cos of theta minus, because you flip the sign, it's plus here, so you get a minus sine of theta times sine of theta, so you're really getting cos squared theta minus sine squared theta. And once again we will sub in for this 1 minus cos squared theta, so I'm going to find that this is cos squared theta minus 1 minus cos squared theta. So that gives me cos squared theta minus 1 plus cos squared theta. That means that, to summarize, we get that the cos of a double angle 2 theta is equal to 2 cos squared theta minus 1, or what I'm really interested in is that cos squared term. I can write this as 1/2, if I solve for it. It'll be 1/2 plus 1/2 cos of the double angle, and this then I can sub in for that term here, because it's a lot easier to integrate something like cos of a double angle, whereas trying to integrate cos squared isn't that easy. Okay, while we're at it, let's do the other double angle that we're going to need here. So that is sine of theta plus theta is equal to sine of 2 theta, and if you go back to this formula up here, that is says that sine of theta times cosine of theta, and the sign is preserved, that's a plus, so it'll be plus sine of theta times cos of theta, so you're actually getting 2 of those. You're getting 2 sine of theta cos of theta, and so I'm just going to note that here because we're going to need that result here in a second as well. So let me put a little box around this as an aside, and we will use those results here in a second. Okay, so let's continue with what we were doing over here. This is equal to 2r squared integral with respect to theta of cos squared. I'm going to sub in a 1/2 plus a 1/2 cos of double angle d theta. And notice that I have a 2 out here and I have 2's down here. Those cancel. So I'm going to get an r squared integral with respect to theta of 1 plus cos of the double angle d theta. And now this is something that I can integrate without any real difficulty. So let's do that. So we get, this is r squared. When I do the integral, I'm going to get the integral of d theta, that's 1 times d theta, is just obviously theta. And then when I integrate cos of the double angle d theta, I'm going to get a half coming out of that. And then I get sine of 2 theta. And I'm not going to pick up a constant of integration because we were using this theta variable as a placeholder to tell us that in fact we have limits on our integral. So this is not an indefinite integral, but it's really a definite integral. But the one thing I want to do is I really want to convert my variable back in terms of y, which is what we started with, because y, if you'll remember, ranges between h and r, and that's a lot easier than trying to deal with arc trigonometric functions and so forth. You can do that if you want, but I would rather put everything back in terms of the variable y. And now the question is, well, how do I go back? So here's the question. How to convert this back in terms of y. Okay? And in fact, it's not too difficult to do that. What we do is we recall what we said y was in terms of theta, and here it is. We said from the very beginning that y equals r times sine of theta. Remember that? So I'm going to say, well, since y equals r sine of theta, then of course solving for sine of theta in terms of y, we find that it's y over r, and the picture on this is a right triangle. Such that this angle theta, if you were to do the sine of theta, it's opposite over hypotenuse. Okay, so think of this as opposite over hypotenuse. And so opposite the angle theta is going to be the y, and the hypotenuse is going to be the r. And by the Pythagorean theorem, then you can say that this third leg on that triangle is going to be r squared minus y squared. Let me put a therefore in front of that to indicate that that's what we solved for. And so now we know that sine of theta is y over r. We know that cos, so therefore cos of theta is going to be, this is going to be adjacent over hypotenuse. So the adjacent over hypotenuse is going to be radical r squared minus y squared, and that's over the hypotenuse, which is r. Okay, so we've got that result here. And one other thing that we will need is to know what is theta. And theta from here, if you solve for theta, you'll find that theta is equal to arc sine of y over r. And so let me put a box around it. Okay, so I think we've got all the pieces to our puzzle here. And now it's a matter of going and finishing up this conversion. So I'm going to do that over here. Down here will come. Okay, so we have, of course, all of this was with respect to the the area of that portion above the chord, which we are denoting as a sub c, is equal to r squared times theta plus a half of sine of 2 theta, and all of this was going to be done with respect to theta. I'm going to use this result here to sub in for what I'm calling sine of a double angle, to put it back in terms of just a single angle instead of a double angle. So I get r squared times theta plus a half of 2 sine theta cos theta is what sine of a double angle is, and that's with respect to the variable, the limits of integration on theta. And now you'll notice once again that I have a 2 here and a 2 there, so those cancel. So I see that this is r squared times theta plus sine of theta cos of theta, and this is all with respect to the angle theta. And then now we're now in a position to use the results we boxed here in red. So let's go ahead and make that conversion, and I'll do that. I'll say converting in terms of y, I get, oh, by the way, before I do that, let me write one more step. Let's distribute the r in here. So I get r squared times theta plus r squared sine theta cos theta, and this is with limits with respect to theta. And so now let's go ahead and make the conversion in terms of y. So I get r squared, and theta we said is that value right there. It's arc sine y over r plus r squared sine of theta we said is, you can't see it right now, but it's right here. Sine of theta is that term right there. It's y over r. So it'll be y over r, and cosine of theta is right over here. So that is radical r squared minus y squared all over r. And now I have to change my limits back to y, since everything's in terms of y, and y, as you'll recall, ranges between h and r. Okay, so we're almost home on this, so it's a matter of plugging in our limits. So this is going to be on the uppercase, it'll be r squared arc sine of r over r plus r squared, oh, by the way, this r squared gets these r's on the bottom. We have two of them, they knock each other out, so I get y is going to, of course, in the upper limit it's going to be r, so that's going to be r times radical r squared minus r being squared. This is the upper limits minus the lower limits. The lower limits is going to be r squared arc sine of h over r plus h times radical r squared minus h squared. And now we notice a couple of things. First of all, I think the first thing that we see is r squared minus r squared is going to be 0. So that term is gone. The second thing we notice is that the arc sine of, basically this is 1, okay, the arc sine of 1, let's remember what that would be. we can draw a little picture of the sine curve. Okay, so here is 2 pi, here is pi, here is where sine is 1, and so that corresponds to an angle of pi over 2. So all of this is pi over 2. Okay, so we're getting close, right? So we can say that this is equal to r squared times pi over 2. Now I'm going to distribute this minus in. Okay, so this is going to be minus r squared arc sine of h over r minus minus h times radical r squared minus h squared. And so really that is it. Let's summarize this therefore. So we say therefore the area of that portion of the circle above the chord is going to be, let's write it first as the original integral. It's 2 times the integral, we said y going from h to the radial dimension r, times r squared minus y squared dy, and when you evaluate this integral you find that it's equal to pi r squared over 2 minus r squared arc sine of h over r, and then minus h times radical r squared minus h squared. And let me just draw our attention to something important here. You'll notice that, before we leave this, you'll notice that this term right here, I hope you'll notice that this is just the area of the semicircle, right? So if I were to draw the circle, and we had a chord up here, and this is the area of the semicircle, meaning if I were to do this in red, it would be all of this stuff. So I'm taking away from the semicircle this term as well as this term. So you can see, I hope you can see that, in fact, these two terms over here, back here, these two terms are the area. Okay, so let me draw the circle one more time. Here's the circle, here's the chord. This portion of the circle right here, the area of this is going to be r squared arc sine of h over r plus h times radical r squared minus h squared. So when you take this area away from the area of the semicircle, you get back the area of the blue shaded portion that we were interested in, which we were calling the a sub c, which is of course given in that formula there for you. Alright, send me your questions if you have any. I hope that made sense to you and hope it was of some benefit, and we'll see you in a future video. Take care.